The coordinates of a point come in a pair of two numbers, a horizontal x component and a vertical y component. Point A has a horizontal x value of 0 and a vertical y value of 6. So the coordinates are 0, 6. Point B has a horizontal x value of -2 and a vertical y value of 0. So the coordinates are -2, 0. C has a horizontal x component of 3 and a vertical y component of 0, so the coordinates are 3, 0. There is a useful fact about quadratics which will help us here. If a quadratic, f of x, has roots r1 and r2, then f of x is equal to x minus r1 times x minus r2, or f of x is equal to minus x minus r1 times x minus r2. The only difference between these two options is the minus sign. The first case is for happy face quadratics, where the function shoots upwards in both directions. The second case is for sad face quadratics, which goes downwards in both directions. Since our function resembles a sad face, we will use the second option. F of x is equal to minus x minus r1 times x minus r2. The roots of the quadratic are the locations where the graph crosses the x-axis. In our function, the roots are -2 and 3. So these are the values for r1 and r2. Let's sub these values into the expression we had. We can simplify by noting that -2 is the same as +2. Now we can multiply out our brackets. X times x is x squared. X times -3 is -3x. +2 times x is +2x. And +2 times -3 is -6. Now we can clean things up a bit. -3x plus 2x is -x. To finish off, let's deal with this minus sign outside our brackets. This has the effect of changing the signs of each of the terms inside. So we get -x squared plus x plus 6. And now we're done, since this is precisely the expression we were asked to come up with. Finding the minimum or maximum point of a function involves a few steps. First, we differentiate the function. Then we set the derivative equal to 0 and solve. And finally, we'll sub back into the original function. From part B, we know that we can write our function as f of x is equal to -x squared plus x plus 6. To begin, we'll need to differentiate this. Whenever we are adding or subtracting terms, we can differentiate each term individually. So we can tackle the -x squared, the x, and the 6 separately. Let's start with the -x squared. We have a rule for differentiating powers of x, which says, multiply down by the power, then reduce the power by 1. The power here is 2, so we multiply down by 2, and then reduce the power from 2 to 1. This gives us minus 2x. To differentiate the x, we can use a rule which says that for any constant k, k times x differentiates to k. We have x, which can be thought of as 1x, so this will just differentiate to 1. Finally, let's deal with the plus 6. There's a rule which says that additive constants simply differentiate to 0. In other words, they disappear. So differentiating the 6 makes it disappear. We're now on to step 2. Set the derivative equal to 0 and solve. We found that the derivative is minus 2x plus 1, so let's set this equal to 0 in an equation. To solve for x, we need to isolate it all by itself on one side of the equation. To do this, we'll need to get rid of the minus 2 in front of it and the plus 1. Let's start by removing the plus 1. This represents addition, so to get rid of it, we should subtract 1 from both sides. The minus 2 in front of the x represents multiplication, so to get rid of it, we should do the opposite. We should divide both sides by minus 2. Calculating our right-hand side, we get our answer that x is equal to 0.5. We've now found the correct x-coordinate for our point. To find the y-coordinate, we'll need to sub back into the original function f of x is equal to minus x squared plus x plus 6. Since x is equal to 0.5, let's replace both x's with this number. Typing this into our calculator gives us an answer of 6.25. And this is the second coordinate of our point. So we found that our maximum point is 0.5, 6.25, which is precisely what we were asked to show.